there is a limit to how large a monster can grow. Even in the universe, physics enforces a ceiling. For a black hole feeding on a disk of gas, the mathematics are clear. Once it reaches roughly 50 billion times the mass of our Sun, it should starve. The blinding pressure of its own radiation blows its food supply into the void. The equations do not bend. The largest monster we had ever found, an abyss called Ton 618, over 40 billion solar masses, seemed to prove it. But 5.7 billion light years away, there is a shadow that may have broken them. At the core of one of the most violent galaxy clusters ever discovered sits something so massive it has no right to exist. An abyss estimated at 100 billion suns, double the theoretical ceiling. A structure so impossibly massive that it sits at the absolute edge of what our physics can comfortably explain. But the terror of Phoenix A is not just its size. It is what it has failed to do. It is an executioner that lost control. Let's begin. To understand why Phoenix A breaks our intuition, you have to understand the war that happens when a black hole feeds. We tend to think of black holes as cosmic vacuum cleaners, instantly sucking up everything around them. But space doesn't work like that. When gas and dust are pulled toward a singularity, they don't fall straight in. They spiral. They form an accretion disk, a massive flattening ring of material swirling toward the center, like water circling a drain. And as that material gets closer to the event horizon, it accelerates. The gas whips around the black hole at an appreciable fraction of the speed of light. At those speeds, the friction is unimaginable. The gas rubs together, superheating into plasma. It reaches millions of degrees. And when plasma gets that hot, it shines. It radiates light and energy outward into the universe. This is where the war begins. Gravity is pulling the material inward, but the blinding radiation of the plasma is pushing outward. Light has momentum. It exerts physical pressure. As a black hole eats faster, its accretion disk gets hotter, and the light pushes outward harder. Eventually, you reach a breaking point, a point where the outward pressure of the light perfectly matches the inward pull of gravity. This is the Eddington limit. If a black hole tries to eat any faster, the radiation becomes so intense that it literally blows its own food supply away. It pushes the incoming gas out into space. The black hole's own feeding creates a pressure that starves it. It is a built-in braking system, a mechanism the universe uses to keep monsters in check. And because of this limit, astrophysicists calculated a theoretical ceiling for a luminous feeding giant, around 50 billion solar masses. If a black hole ever reached that size, the accretion disk required to feed it would have to be light years across, and a disk that wide is inherently unstable. At the outer edges, the gravity of the black hole would simply be too weak to hold the gas together against its own rotational speed. The disk would fragment, collapsing into stars instead of falling into the abyss. 50 billion suns. That is the ceiling for a black hole growing by eating gas. But the universe has a loophole. Black holes can merge. They can collide in the dark, bypassing the feeding limits entirely. And something in the southern sky suggests that is exactly what happened. In 2010, astronomers looked deep into the cosmos and detected a massive grouping of galaxies bound together by gravity. The Phoenix Cluster. It is one of the most massive galaxy clusters known. A chaotic, swirling ocean of hundreds of galaxies bound together by dark matter, all suspended in a sea of superheated intergalactic gas. You have to understand the violence of this environment. The Phoenix Cluster is not a quiet neighborhood of the cosmos. It is one of the most hostile, chaotic regions of space we have ever observed. It is the most luminous X-ray cluster ever discovered. The space between the galaxies here isn't empty. It is filled with a churning fog of plasma, heated to tens of millions of degrees by the sheer gravitational friction of galaxies grinding against each other. It is a furnace. And at the exact dead center of this maelstrom sits a single massive galaxy, the anchor. And at the center of that anchor, there is a shadow. When astronomers studied the extreme density of stars in this core and modeled the sheer energy required to shape the surrounding gas, the numbers didn't make sense. The models demanded a gravitational anchor of terrifying proportions. The black hole at the center of the Phoenix Cluster wasn't just large. The models pointed to a mass of 100 billion suns. 100 billion. Sagittarius A star, our black hole, is 4 million solar masses. Ton 618, the monster we once thought was the absolute ceiling, the abyss that seemed to break the scale, is over 40 billion. When we looked at Ton 618, it felt like looking at the final boss of the universe, an object so large it defied comprehension. If the estimates are correct, Phoenix A dwarfs them both. It required a new classification. Astronomers propose calling objects of this magnitude stupendously large black holes, slabs, a category invented because the old words were no longer big enough. But numbers like 100 billion lose their meaning. The human brain cannot process them. To understand the dread of Phoenix A, you have to map the physical space it occupies. Every black hole has an event horizon, the boundary line where escape velocity exceeds the speed of light, the point of no return. For a black hole with the mass of our Sun, that boundary is a tiny sphere, just 6 kilometers across. For Phoenix A, the event horizon could have a diameter of roughly 590 billion kilometers. Let that distance settle. If you were to take Phoenix A and place it at the center of our solar system, it would not just swallow the Sun, it would swallow the orbit of Mercury, and Venus, and Earth, and Mars. It would swallow Jupiter, Saturn, Uranus, and Neptune. It would swallow the Kuiper Belt. It would swallow Voyager 1, which has been traveling at 38,000 miles per hour since 1977. The darkness would reach the inner boundary of the Oort cloud. Our entire planetary system, everything we have ever known, every probe we have ever launched, would be lost somewhere deep inside the interior of the shadow. The geometry of this abyss is suffocating. Light is the fastest thing in the universe. It crosses the distance from the Earth to the Moon in just over a second. But if a beam of light could somehow travel safely across the diameter of Phoenix A's event horizon, it would take weeks just to reach the other side. Weeks of traveling at 300,000 kilometers per second just to cross the shadow. And because the boundary is so unfathomably wide, the curvature of space-time at the very edge is surprisingly gentle. If you were in a ship drifting toward the event horizon of Phoenix A, you would not feel a sudden, violent pull. You would not be stretched into spaghetti. The tidal forces at the edge of a 100 billion mass black hole are weaker than the gravity you feel standing on Earth. You would cross the point of no return, completely intact. But before you slipped into the shadow, your eyes would witness a fracture in reality. Just outside the event horizon is the photon ring, a boundary where gravity is so powerful, yet so precise, that it forces light itself to loop around the hole multiple times before escaping. If you were drifting through this layer and looked out into the void, you would not see a clean reflection. You would be surrounded by infinite, highly distorted echoes of the entire universe, bent and shattered by gravity, suspended in a sphere of trapped, ancient light. And then you would cross the line. You would slip into the dark and you would not even know it. And then you would fall. But the most unsettling truth about crossing the event horizon is what you would actually find inside. We imagine a black hole as a solid sphere of darkness, packed densely with crushed matter. It isn't. The mass of 100 billion suns is not spread out across that 590 billion kilometer shadow. It is entirely concentrated at a single, infinitely small point, at the exact dead center. The singularity. Which means the vast majority of Phoenix A is just empty space. A hollow, pitch-black cathedral, hundreds of billions of kilometers wide. You are not falling into a physical object. You are falling through an empty room, being pulled toward a speck of dust that weighs more than a galaxy. Not for a minute, not for an hour. Because the distance from the event horizon to the singularity is so vast, you would fall in the absolute, perfect dark for a matter of weeks, falling in silence, waiting for an end that refuses to arrive. Usually, a supermassive black hole is an executioner. When a black hole sits at the center of a galaxy cluster, it acts as a heating mechanism. As material falls in, the black hole blasts out intense radiation and relativistic jets of plasma. This violent energy heats up the surrounding intergalactic gas. And heat is the enemy of creation. For a star to form, a cloud of gas must be cold enough to condense and collapse under its own gravity. When a black hole superheats the galaxy, the gas cannot condense. It cannot collapse. Astrophysicists call this process quenching. The black hole essentially sterilizes the galaxy. It shuts down the stellar forge, enforcing an aging, dying population of red stars that will slowly burn out in the dark. That is what is supposed to happen. That is the natural order of a galaxy cluster. But Phoenix A is broken. It is an active galactic nucleus, firing massive twin blowtorches of relativistic plasma from its poles. These jets punch into the intracluster medium, carving out massive hollow cavities tens of thousands of light years across. But for a cluster this massive, these jets are simply not strong enough. The executioner has failed. The heating mechanism that keeps every other massive galaxy cluster dead has broken down. And without that thermodynamic check, the universe takes over. A runaway cooling flow has begun. The gas is cooling rapidly, especially in the turbulent wakes behind the cavities carved by the jets. And in places, the black hole's own outbursts may be making things worse, helping the gas cool along the edges of the very cavities they carved. And when gas cools, it collapses. Instead of sterilizing the galaxy, the failure of Phoenix A's braking system is allowing cold gas to flood inward, unchecked. In the Milky Way, our galaxy is quiet. We produce about 1 or 2 solar masses of new stars every year. A slow, peaceful drip of creation. At the center of the Phoenix cluster, the cooling gas is condensing into the equivalent of roughly 700 solar masses every single year. It is among the most intense starbursts ever recorded in the center of a galaxy cluster. Phoenix A is not a conscious architect. It is a tragedy of physics, a localized, hostile machine that cannot control its own gravity well, blindly flooding the dark with new stars because it is incapable of shutting the stellar forge down. But the existence of Phoenix A leaves us with a terrifying problem. If the models are right, and Phoenix A approaches 100 billion solar masses, how did a black hole get this massive? To reach 100 billion solar masses, a black hole cannot simply eat gas. Even over billions of years, the intense radiation of the Eddington limit would act as a chokehold on its own growth. Which means the origin of this monster requires a much more violent pathway. Some physicists believe the seeds of these monsters did not grow from dead stars. They point to direct collapse black holes. In the extreme chaotic environment of the early universe, just a few 100 million years after the Big Bang, the rules were different. The universe was clean. There were no heavy metals, no carbon, no oxygen, no iron. Just massive, pristine clouds of pure hydrogen and helium gas. Clouds hundreds of thousands of times more massive than our sun. In the modern universe, Gas clouds like this cool down, fragment into smaller pieces, and ignite into thousands of normal-sized stars. But without heavy metals to act as a coolant, those primordial clouds couldn't fragment easily. They stayed whole, and they grew heavier. Some theories suggest that these massive clouds never bothered to ignite. The entire cloud reached a critical threshold and simply caved in. All at once. Tens of thousands of solar masses collapsing straight into the dark in a single catastrophic instant. There was no brilliant flash of light, no supernova, no warning. Just a cloud of gas that got too heavy and instantly became a tear in the fabric of space-time. These massive seed black holes would have a terrifying head start. They roamed the early universe, merging with other monsters in the dark over billions of years, bypassing the feeding limits entirely to build the stupendously large black holes we theorize today. Or perhaps Phoenix A is the result of a more recent, apocalyptic merger of dead giants at the exact center of the cluster. We don't know exactly how it was made. $5.7 billion light years away, in a darkness we will never cross, the runaway forge is burning right now. Hundreds of solar masses igniting every year, pulled from cold gas by the failure of something that was supposed to destroy. But the tragedy of this failed executioner is that eventually the fuel will run out. The massive cooling flows of gas raining down into the center of the Phoenix cluster will begin to dry up. The accretion disk will thin out. The massive jets carving out the voids will sputter and slowly shut down. The starburst will end. And when the gas is gone, Phoenix A will stop growing. It will sit at the dead center of a massive web of galaxies it accidentally populated. The massive young blue stars will burn through their fuel in mere millions of years, dying in violent supernovae. The smaller stars will slowly age, redden, and eventually burn out into cold, fading embers. And the black hole will simply wait. An object of unimaginable mass, sitting in absolute silence, outliving the very stars it allowed to exist. It will wait for trillions of years, long after the rest of the universe has gone completely dark. And the geometry of its shadow will remain 590 billion kilometers across. If you were to arrive then, at the absolute end of time, drifting alone toward that gently curving boundary, nothing would feel like a sudden, violent snare. Nothing at the edge would tear you apart. You would slip across the event horizon of the absolute abyss, and you would fall into the perfect, unbroken dark, falling for weeks in total silence, waiting for an end that refuses to arrive.